on my presentation. So I can take the liberty of cutting it down significantly, maybe by about half an hour. And actually, there are going to be multiple talks on the same topic. So whatever details that I'll just sort of flash through here, more details will be available. And of course, I'm here around to talk more about the project. So I will set you free at 1. Make sure that you have your lunch before Jummah, because that is the time that you will have some open space in the dining halls. Otherwise, it will get very crowded after Jummah. So that is why we are trying very hard to finish the session today at this session at 1, so that you can go have your lunch and then go for Jummah. Okay? So just to be aware of. And any other thing that you want to actually discuss or pinpoint. I mean, the organizers are here, Sajjad is here, so please feel free. Okay, so let me actually start this presentation, which again I'll try to cut down and finish by 11:30 if possible. We'll have a small tea, and then Professor Burns will be presenting. So this is about this NI landmine detection competition that, as Dr. Awais has just broke the news, we have actually won. And the project was actually very, very interesting. And we learned several things in several areas, and this was sort of exactly the sort of activity that we were looking at to actually seed this whole area of robotics inside LUMS. The outline of the talk is that I'll just tell you about what this project was all about, where this actually came from, the brief history. I'll introduce you to the team. The team members you looked at, for example, from my lab, not all of them are there actually. So there were actually 10 people who, over a span of 2 years, who actually worked on the project. The team members that you saw in the last slides was actually maybe some. So it was a little bit out of date. Something about the design overview, infrastructure backbones, very briefly describing the mechanical design, the software backbone, the sensors, and the main subsystems. Again, there are going to be multiple talks on this in this workshops. You will have some more tasks, some critical tasks. So I'll just pick 1 or 2 tasks, which I thought was most critical and where we actually achieved the most, and which actually made the difference between us and the rest of the team. And some experimental results. So very, very quickly, the menace of landmines, as we all know, 76 countries worldwide are actually affected by landmines or unexploded ordnance. It's a big menace. Pakistan itself is actually a victim of this. As you know very well, there's a disturbance in our northwestern regions, and because of which there is a proliferation of these landmines in many, many areas. In fact, one of the surveys, the source is not cited here, but I can give you that if you ask me. So between 1999 and 2009, about 2,400 casualties due to landmines happened in Pakistan. And more than 3/4 of those were actually civilians. So, I mean, this is actually something to be really concerned about. And then one thing that exasperated the situation last year was that actually the floods, they carried landmines from war zones to non-combat zones. And actually this is one picture of a media report that was showing these landmines being actually driven by these flood waters to lower areas. So, I mean, it's a huge problem. And the context of this particular situation was not Pakistan, but actually Lebanon. Well, it should be misspelled here. Lebanon doesn't have those spellings, but anyway. So it's a small country, as you can see, but bordering one big neighbor. And as you all know, that there is a frequent war. So, for example, as late as 2006, there was the Hezbollah-Israeli war, and the border between Israel and Lebanon that is actually just totally infested with landmines. So, according to their estimate, 150 million square miles since 1975 has been planted with landmines. And 45% of that area still remains to be cleared. So, that is actually a huge area. And their estimate is that about maybe 500,000 of these landmines are there, and tens of thousands of just unexploded ordnance like cluster bombs or whatever. They are just spread all over the terrain. So, it's not really possible by the Lebanese army or their counterparts to actually clear those things just manually. So they actually teamed up with National Instruments, the Arabia division. Now, National Instruments, as you may know, is actually the global leader in instrumentation and control. I mean, the robotics is not really their area. They've just moved into robotics, but they are really one of the one of the sort of leading companies in the world that supplies these instrumentation control kind of equipment. Now, their Arabia division, which looks after North Africa, Middle East, Pakistan, including Turkey, and they actually announced a competition in collaboration with LabMac, which is the Lebanese Mine Action Center. And this LabMac actually is actually a subdivision inside the Lebanese army, which actually clears the mines. And they announced the competition in 2010, early last year, to design, of course, a robot for the detection of landmines and cluster bombs. Now, as Carson, and people, experts like him know, this is not really a trivial task. And in fact, when you say, well, you design a robot and for the detection only, and remember that this is just detection, not the manipulation or the diffusing of the mines, just the detection part. This is a really, really hard problem. So nobody really expected that you would actually come out with a solution that would be deployed in 1 year, but they wanted to test the technology. And they also wanted to see, well, what can countries like us do? Okay, so as you can see, the Arabia division, it does not cover the Europe or US. In fact, robots like the one, for example, shown in white on the big fly, the PAK-Bot, that is available to buy for like $50,000 or something, which can very slowly do something, but maybe not affordable. You cannot really scale those kind of things. So they announced this competition, and then we actually thought, well, maybe this is the opportunity that we were sort of looking for. Well, it's a very humanitarian cause, real application, will give us the chance to show to the world what we can do. Okay? And at that time, actually, there was no experimental robotics base in our sort of group. I myself am from a completely theoretical background. This was my first experimental robotics project as well. So we teamed up with RICE, which has significant experience with robotics. Dr. Vyas actually is missing. Yeah. He's actually a mechanical engineer by training, and also now moved into computer science. So we thought this would be a very nice combination. Let's send an entry. So we sent an entry, and the phase 1 was basically just concept papers. 10 teams were selected in that first phase. I think from Pakistan, 2 teams were selected. So I think 1 team from NED was also selected. So that was actually, I think, again, a very nice distinction for Pakistan, that not 1, but actually 2 teams were selected from the initial concept papers. Of course, we were among them. Phase 2 was that they asked for design proposals. Okay? And that was actually full proposal outlining your mechanical design, how you're going to execute the software. Nothing has been built yet, but they wanted a very detailed proposal on what can be done. And they announced 5 finalists, and of course, we were one of the finalists. Now, what they did was that they gave to each of the finalists significant, healthy contribution to buying equipment. Now, of course, their finger in the pie was that they wanted their tools to be used, so they actually donated their own controllers and smart cameras and so on and so forth, roughly about $40,000 equipment to us. And then LUMS was very, very generous, that at around the same time, there is an internal faculty initiative fund, which is every year, where LUMS faculty can compete for small grants, about 8 lakh rupees or maybe $10,000, so whatever way you want to put it. And we were again very, very lucky to actually win one of those grants. So combining these resources, maybe the salaries, the mechanical design coming out from this grant, and the equipment donated by LUMS, we actually embarked on this project about middle of last year. Okay? And phase 3 was actually the real thing, which happened just last week. And these were real trials in Beirut, in an actual arena where landmines were actually buried, and we had to ship our robot there. Big story on how the shipment took place and all. But even before that, so this was basically dedicated work of about 1.5 years of about 10 people working on different areas. And so the big news is that Pakistan won that competition. And I think that was a really big honor. And I want to say this, that Pakistan won, not just that LUMS won, because if you look at the team here, so I will just very shortly introduce the team. So I was the lead, Dr. Vyas was the co-lead, Sayyid Abbas, Musa as we call him, he was the lead with the software. Talha was leading the visual surveying part. Adnan was the lead in mechanical design. We had our lead machinist, Zahid. Sayyid Abbas, who did the power electronics. There is Sufyan, There is Moekab, who did the initial design. Ali Abbas, Dr. Abbas's student, helped with the software architecture. Hassan, he did the initial things on NI tools, and then Atif, of course, did some electronics. Again, well, the reason that I said that this was Pakistan, because if you look at their backgrounds, these people have been with us for maybe 2 or 3 years, but 3 of them are, well, maybe I should count, 1, 2, 3, and 4. 4 of them are from NUST, EME. Okay. And if you look at, for example, Sayyid Abbas, and who else? Who else is from FAST? One person? Right? Okay, so I mean, we are getting a person from FAST. And then Adnan here is actually a care former student. Okay, so we have yet to have our own students, because our own batch is actually graduating soon. But these are the best of the best gathered from all over Pakistan. They come here to our group, train with us for 2 or 3 years, and then they produce these things. So that is why I dedicate the win not to just LUMS, but to all of the institutes that have actually helped produce this material to help us win this thing. Okay. So the robots that actually participated in this thing, interestingly, the design was not about just one robot, but we actually just went a little bit overboard and said, well, we are going to just design many, many robots which are going to work together. There are going to be some scout robots, there are going to be some main robots, they're going to make a swarm, and that is how we're going to solve the problem. So the main robot was actually the Marwa mine detector. It has this capability. Again, I will not be very going into the details, because there is going to be full talks on all this. Our main scout robot was Duldul. This was mainly for scouting out, doing the mapping, and so on and so forth. And these are real terrain robots, ability to move in rough terrain, not indoor type things which can get stuck even on a carpet. Then we also had some robots to test out some algorithms, for example. So we actually had developed our own telepresence machine to, for example, test out some SLAM type algorithms and some software architectures, and to do the multi-robot to test out some things on the, for example, communication and so on and so forth. We have about a fleet of 4 Roomba robots. So that also is something that we frequently use throughout the project. Now, again, very interesting something about robot names. Again, this will take a while. I'll not go because there's a lot of details coming up. The names were very interesting. I just want to quickly mention that these names were not by me, but actually by the students. Marwa is named, as you may know, Safa and Marwa. That's one thing. The real reason that we named the robot as Marwa was because Marwa is the name of that 10-year-old Turkish girl who donated her year's salary to Pakistani flood victims last year and sent a letter to President Zardari. I think all of us remember that story. So out of our token of thanks or whatever, we named our main robot as Marwa. Duldul, I don't know how many people, does anyone know what Duldul means? Duldul, nobody knows? Okay, again, named by one of our students. So this was the Prophet's mule, one of the animals that was used by the Prophet Sallallahu Alaihi Wasallam. So because it was sort of very sturdy and going on. And Safa, of course, to couple with Safa and Marwa. And then there's a story behind Hanun, which I will not go. Okay, so I mean, this is just to see. I mean, we had some fun with this project. Okay, so what were the design objectives with this project? Well, one thing that we actually very heavily emphasized was that there were people like, for example, Carsten Burns here and groups like them, working on these similar things for over 20 years. Base that they have, a very solid base, and so say a whole army of people working on many things. We cannot really go to that point in just 1 year. Okay? So we had to do things in a very different way. So what we said was that we are going to go after designs which are going to be very affordable, okay, indigenously produced, and we are trying to sort of aim at things, at technology which can be not only produced and deployed, but maybe replicated in a developing world country by small budget organizations, meaning that if some NGO or maybe a district government wants to buy that robot, it should be affordable to them, not the $50,000 PAK bot that only Pakistan Army or the Lebanese Army can buy, maybe in small numbers. Okay? So that was one thing that should be very affordable. Just cut down the cost really. And also it should be extremely simple. Okay? We do not have either the capability or in fact not even the inclination to make very complex machines. So it should be as simple as possible using commercial off-the-shelf open source tools. Again, Carsten, as you as well as shortly explained. And they have spent decades developing simulation tools, so on and so forth. We don't have the time to do that. Let's look at what is available out there in open source, and let's reuse all of those things. Scalability, of course, because we wanted this thing to be deployed on a very large scale. So if your organization want to do it for 1 mile, fine. But if you want to scale it to, say, 100 miles, then the solution should be scalable. And then the other things were basically, and the most important thing was to the rule compliance. So there were a number of rules that we had to follow, and so that was one constraint by which we had to do this. Now, interestingly, now this is where our design was sort of caught their eye. There was a small economic analysis of what would be an affordable robot. So, well, what we looked at was that maybe in developing countries like Pakistan, you can actually hire a year. Do not give any health insurance, nothing. I mean, you can just bring people in, you set them inside the minefields, and if they, God forbid, blow to pieces, nobody's responsible for it. And believe it or not, that's how many organizations are actually working. I mean, call it human exploitation or whatever, but maybe that's the only option, because there is no mechanism. It's bring in the robot, but then the whole army of people who are actually trying to operate the robot. The cost is actually astronomically high. So those kind of approaches, those kind of PAK bots or whatever that you want to call it, I mean, those are not possible to do. So the dilemma for us was that if we go after very complex solutions, of course, the cost becomes really high. And you need maybe the complex solutions to have reliability, because the complexity is there for a reason. So if you go for now simple solutions, now it is something that will break down all the time. And we sort of proposed, again, a concept that, well, why don't we not put not just one robot in the field, but actually put a number of them. Okay? So if we have 10 robots in the field, and if they are coordinating, 2 of them have broken down, maybe 8 of them are still working, you bring those 2 back. If 2 of them have not detected the mines very efficiently, maybe there is a chance that the other may go over the same terrain and do something. And we did a very simple reliability analysis. For example, a robot that breaks down 50% of the time, you actually bring in, for example, six robots together, and then you can maybe cross the 99% reliability barrier. Again, this is a very sort of an elementary analysis, oversimplistic, but that was sort of the motivation. And this was how we sort of tried to justify why we are trying to go this way. This is not a very concrete economic analysis, but sort of the way to go. And then when we did the economics, we came out with a price tag that, well, $1,800 per robot, plus you put maybe $600 for the computer, and then okay, this is the budget that we are going to be within, and we are going to develop everything within itself. And as far as the reliability is concerned, well, we are going to put everything, transfer sort of the complexity from the hardware to the software. So we cannot give it the muscles that Kaiserslautern has, but maybe we can give it the brains. Okay, so I mean, and that we again, whatever that we can try within our capacity, we'll try to do. And also, we also very much emphasize that it should not be just a teleoperated machine, because in fact, the competition was sort of leaning towards that they actually did not ask for intelligence. But we said, no, if you have maybe 8 or 10 machines working in parallel or something, yeah, you need to have those machines very much more autonomous than just simply somebody walking them through via a video link or something. Okay? So you have to bring in a lot of autonomy into them. So that was really our objective to start with. Now, admittedly, we, as you will see now, we may not have gone exactly to a functional 10 robot system on a field doing everything, because the technology is very hard. But we actually bumped into a lot of surprises, and very pleasant surprises. Okay? So the design overview is as follows. Again, I will be very quick. I'll just give you some outline of the mechanical design, some sensors, drive, and control hardware, software architecture and supervisory control, and the multi-robot coordination part I have to skip. Now, this was the entry that we actually sent. Okay, this is the final thing. Now, unfortunately, the robot is now on its way from Lebanon to Pakistan, or we would have loved to show you. I asked the organizers very much that we would like to showcase the robot here. It's still somewhere stuck in the airline, so it will be unfortunate. But we will display this, and people from Pakistan, you are most welcome to see this. Now, as you can see, this is inside the lab. It's a mess. it's not as beautiful as your robots, Carsten, but nevertheless, it's there. So it's basically a simple vehicle kind of a thing on which a mechanical arm has been mounted. there is actually a stereo vision system which is guiding the arm. Okay, and there are these RGBD cameras, i.e. Kinect, the Xbox sensors which have just come in for the main navigation part. There is power electronics back there. There are the NI donated controllers which are maybe hidden somewhere behind the arm. That's where the sensor payload is mounted. And yeah, these are the two pieces. So we had two PCs actually controlling the vehicle. So one PC was actually controlling the vehicle and one dedicated to the arm itself. It's a very complicated sort of a multi machine thing. And all of them, of course, communicating with each other to do something. Now, the hardware resources was that, again, if you start from the two PCs, one PC was just dedicated to stereo vision as well as connecting to SBREO, the main controller. Again, we don't have the fortune to have, I mean, the embedded systems we had to procure from somewhere by, so this was sort of donated to us by NI. Nevertheless, making it work was one I mean, non-trivial task as well. So this was sort of our low-level main control. These were sort of high-level controls. So this system, the PC, the low-level control, and the stereo vision, this was controlling the arm. There were these NI smart vision cameras. Each camera by itself actually is a computer, which just sends out a report maybe to the to its master machine of what it has done, but you can implement full-fledged machine vision algorithms inside here. The other PC was actually doing the SLAM algorithms connected to the Kinect, the RGBD sensor, maybe the GPS, and then reporting the, doing the map and also the wireless communication. So this was sort of the master controller in some sense. And then there was the power electronics. Now we had to actually put in separate microcontrollers controlling the motors as well, because we wanted to bypass the main electronics. Supposing that everything fails, then there should be a way of bringing the robot back by just simple remote control. So teleoperation was also possible. Then of course battery, and then a metal detector. Again, we did not go for a very, very sophisticated metal detector because that's very difficult or expensive to buy. I just bought a metal detector off a toy shop actually in one of the malls in the Middle East, and that actually worked for a basic demonstration. Okay, and one thing which we did not incorporate actually was the IMU. It has not arrived as yet. The reason for that was that if, for example, the robot platform is actually doing roll, pitch, yaw kind of motions while going over bumps or whatever, then the arm movement it is really critical to adjust the arm movements according to how the platform is. So that was necessary, but that was not included in time. In the next phase, hopefully, we'll do that. The main computing resources there was one PC which was running Linux, and on top of that was the ROS architecture. Again, there will be a full talk on this platform. Again, if you do not have the army that Carsten has, maybe you can get up to speed and running with basic robotics projects using this framework. So that was one motivation of using this, plus using OpenCV, PCL kind of libraries, and this stereo cameras. No, this is not the stereo, but the Kinect part. So this was sort of doing the mapping and localization part, and the vehicle control, autonomy, navigation. Then there was another PC which was running Windows plus LabVIEW, communicating with SBREO, the stereo camera interfaces running open. So this was the visual servoing part. And then there was, of course, the SBREO running VxWorks, the low-level controls, and then the NI smart vision cameras. Again, admittedly, we did not actually put this part into much use, but architecturally, this was all there. I mean, there was no problem in. And we chose a LAN as the basic communication. Now, this was the software data flow. Now, some of this actually changed by the end, because by the end, as you all know, I mean, there's projects evolve, a lot happens. But there was a lot of things in this the software modules, and that was one of the reasons that we had to adopt a package like ROS in the absence of a library of, a tool of ours. So we had to take a certain structure on which we had to build this. So there were several things happening on this side. There were multiple actuators, multiple sensors. This was sort of the arm movement control. This was the main vehicle control. And then we also need some data logging kind of capability, system health monitoring, and so on and so forth. So again, it's so maybe the critical modules was the SLAM part, obstacle detection, the depth estimation for stereo, the low-level controls. Maybe one or two parts were not there. So this IMU part, for example, as I said, that this actually we did not have time to incorporate. But what I wanted was sort of an estimator doing a robot self-pose, but this we could not. incorporate in the current version. But hopefully we'll do that. So this was sort of a cartoon of what this thing would be, but nevertheless. Okay, so this was the mechanical design. We designed it to be for double Ackermann kind of steering. In the end, we actually did not use it in the double Ackermann configuration, but so this design was done by Adnan Munawwar, one of our brilliant lab engineers here. We built the robot here at a local machine shop. All the designs were produced in Pro Engineer. The more sort of, okay, so here, I mean, the suspension was very interesting. It